Welcome back to our AP Chemistry Notes, Chapter 11, talking about the topics of equilibrium constant with acids, bases, and we have already started buffers. And there's really not much additional with a buffer. The point is it works like a common ion effect, or if you're doing this first, it is, you will find common ion effect is like a buffer. But one of the things that comes up when we prepare a buffer, and also what comes up when we do a neutralization, a titration, is that we will often be mixing two solutions. So you will need to account for that in your work. So we're going to do nothing but work some example problems so that you can, for the best results, you can pause and work ahead and then play and check your work. And if you are working ahead and get stuck, you play until you're unstuck and then you pause there and continue working. And yeah, that's going to take a while with these notes, but it's going to be so worth it to see what you do know and what you do not know and how to fill in those gaps of what you do not know. So ideally you would be able to work all of these problems entirely on your own with no problem, because we really have covered everything you would need to know for them. But chances are, even with the practice in class, that you are still needing some practice. So that's what this is. This is another chance for me just to remind you of the little detail things that are going to be happening. So we're going to see that, let me get something appropriate to write with. We're going to see how we would consider a buffer solution. And in this case, we're mixing 20 milliliters of 0.10 molar sodium fluoride and 100 milliliters of 0.05 molar hydrofluoric acid, and we have a Ka for that weak acid. And yes, that's what we need, but I want you to catch what's going on here. First off, would we have a buffer? I've got a acid, a weak acid, and the same, see how the same anion there, of a soluble salt. Now with the base, it'd be a cation you look for. But yes, it is going to be a buffer. And so in theory, I could totally use the Henderson-Hasselbalch equation. But I want you to also see what's going on here, and this is really important for you to catch. I'm mixing 200 milliliters with 100 milliliters. So I need to account in my calculations for a total volume of 300 milliliters. That's going to dilute both of these. Okay, so you want to be sure you account for the dilution. The way I recommend counting for dilution is that you take your molarities and your volumes and you turn that into moles. And then you work in moles until you get to the end of the change category, until you get to your equilibrium, and then you convert to molarity. So I like doing the actual reaction part in moles when I have a dilution, and then find a molarity in the end after the reaction. The other option is, of course, to change all of them to a new molarity, M1V1 equals M2V2. So just account for the dilution ahead of time and then just plug it through like normal, and there is that as well. Really can't go wrong either way as long as you account for the dilution in some way, shape, or form. So be sure you do that. Okay, so I have this reaction going on. Okay, so I do have a good color. There's a reaction going on where hydrofluoric acid is going to be in equilibrium with some hydrogen and some fluoride ions. And that's what I'm looking at. I wonder if there's a, I guess not. And so I'm ready to start working in some numbers, but here's what I'm going to do. I'm going to take there's my hydrofluoric acid. I'm going to take my molarity times my volume, and I need to be sure that molarity matches volume, so I need to divide by 1,000 here. Sorry. I need to divide by 1,000 there. And so that times that divided by 1,000 tells me I'm going to start with that didn't work. Am I not on my pen? I'm not on my pen, that's why. 0.00, I'm wanting to double check I have the right amount of 0.005 moles of that. Okay, so I'm working in moles now to account for the dilution. this is 0, and I'm tempted to put, for the fluoride here, I'm tempted to put a 0, but I shouldn't because I have some sodium fluoride. And we know that sodium fluoride is a very soluble salt, so one-way arrow, and it's going to one-way arrow to give me sodium ions, which I don't care at all about, and fluoride ions, which I do. Those sodium ions can just stay floating around in the beaker. I don't care about them. They're spectators, not doing anything. That fluoride ion, I do. Now over here, it's a 1-to-1 ratio, but I'm going to take my 200 milliliters of my 0.1 molar, so molarity times volume divided by 1,000 to convert to liters, and I see that I get, and again I'm wanting to check the zeros, 0.020. Okay, checking my zeros, 0.020 moles. Of that is what I have to work with. Well, if it's a 1-to-1 ratio and it's a one-way arrow, then I'm going to get 0.020 moles of that. So that number is what I'm going to bring over here. 0.020 moles. Okay. Now what's going to happen now that I have some acid and I have some anion going on? Well, it's still going to be a shift to the right because that's what Q versus K would tell me. Calculate Q. It's going to be 0 because there's 0 there. So Q versus K tells me I need to still go from reactants to products. So how much am I going to lose? I don't really know. How much would I gain? Same amount because it's a 1-to-1 ratio. Okay. Now since Ka for hydrogen fluoride is 7.2 times 10 to the minus 4, I'm wanting to sit here and question, is this small enough compared to that number that I can make the assumption and avoid the quadratic? What if I say I don't know? Can I say that? Well, let's pretend I can make the assumption and then we'll just check that pretending later. So I would start by saying assume. Okay, so write your assumption. Assume that blah, blah, blah. Okay, so this, when I assume, remains 0.0050 moles. This is X, and this one I assume, because the same assumption there would work here, 0.020 moles there. Okay, and I will check later if my assumption was a safe assumption. Now, again, I've been working in moles because I have a dilution. Now that I'm done with my work, when I'm done with my reaction, now before I do my calculation, because K calculations must be in concentration, that's why we do all those square brackets. Square brackets must be molarity, must. Those square brackets means concentration in molarity. That's what those mean. Okay, that should be firmly and completely and 100% implanted into your brain. Square brackets must be molarity, which is why it's wrong if you're writing a KP and you're in like atmospheres, you can't put square brackets because you're doing bad chemistry then, so be careful. Anyway, I'm going to divide by the entire volume of the mixed solution. So 200 plus 100 is 300, but I want moles per liter, so I'm going to change that to 0.300 liters. Sorry, the 3 was supposed to be first, liters. Okay, so I do that, and what I get in terms of molarity is 0.0107 molarity of that. Still have X there. And over here I have 0.0666667 molarity of that. Okay, and I'm probably keeping way more sig digs than I need, but that's all right. I'll round them off in the end. Now I write my Ka expression. So Ka is square brackets, because that means concentration and molarity, of hydrogen, of fluoride, divided by hydrofluoric acid. Okay. On the numerator, I have 0.0667 molarity X, because I'm multiplying those. In the denominator, I have 0.0107 molarity, and that's going to be equal to my Ka, which is 7.2 times 10 to the negative 4. So yay, fun calculator time. Oh, so much fun. So I get X, and what I really care about my X can be equal a lot, but what I really care about the X is that it equals the H plus ion, because I'm looking for pH, so I need H in the end to find a pH. I plug that through a calculator and I get that x is equal to 1.8 times 10 to the negative 4. Wow. Okay. So there's my concentration of hydrogen ion. 1.8 times 10 to the negative 4 molarity, because that's what square brackets mean, molarity. And now I want to double check before I continue, was I okay in making the assumption? Okay, so I'm going to take this number and I'm going to subtract that number as if, I was still subtracting there. And I'm going to then re-round to 2 significant digits, and I see that there's no change. No real noticeable change. Not a huge change to what it is. So yes, I was safe in making the assumption there. So that's how I would go about that. Pretend you can assume until your checking tells you you can't, because it's a lot quicker than to go back and just simply redo it with the quadratic equation than to somehow, I guess, do the quadratic equation first and then see, oh, could I have assumed? Because that's certainly the long way around. I have not finished the question yet. I need a pH. Well, we know pH is the negative log concentration of H plus, which means that the pH is going to be the negative log of 1.8 times 10 to the negative 4 molarity. Wow. Go on back. You can do it. Okay. Which means my pH is negative log concentration of H. That's a 4 there. My pH is 3.74. Okay. So there is my pH of this buffer solution, and we did a calculation. We've done many calculations just like this for buffers before. What was unique about this is we accounted for the dilution that happened when we mix these two solutions. So you really want to be careful. If the question says you're dropping in solid, you can assume it dissolves with no volume change, and then you don't have to account for dilution. When you do mix two solutions, there's going to be a dilution. And so, because they rhyme, two solutions give you dilution. And so I account for it by working in moles until I'm done with my Rice table, done with the reaction. And then I convert back to molarities to work into my Ka, because Ka must need molarity. You could have first accounted for it by doing M1V1 equals M2V2 at the very beginning and accounting for it that way. It will work out the same way either way. Okay, let's look at the other one. The next problem. Maybe. There it goes. Okay, so we're going to work this problem, and again, the best thing to do is for you to pause and come back after you've tried it and see how well you did. And if you start working and get stuck, you can unpause for a little bit to get unstuck, and then pause again to come back and work at that. Really, yes, I know it's going to take long, but you don't often have very long homework assignments, and it would be so worth it in the end to work it that way. It will build your ability to handle these calculations much better if you do it that way. So please go ahead and pause and then come back. So I'm looking for grams of ammonium chloride that must be used to prepare 500 milliliters of a buffer solution that is 0.1 molar in ammonia and has a pH of 9.15. So let's start by focusing on our equation. Ammonia, NH3, is going to react with water, which is HOH, and write it that way if you need to see the reaction. It's going to make NH4 plus and hydroxide, which is why we call that a base, because it does end up making hydroxide, which ends up making it basic. All right, so now that I've focused on that, I don't have a dilution to worry about, because I'm just figuring out how many solid grams of ammonium chloride I would dump in. So let's talk about what I'm starting with. I'm starting with a 0.10 molar solution of that. It doesn't matter right now that I have 500 milliliters of it. I'll get to that later. I never care about water. Okay, It doesn't involve our K equations, and it really does nothing. The amount of change to the water in the beaker is so incredibly minute. Don't waste your time doing anything with water. It is truly, literally a waste of time to mess with the water in this case. That is what I'm looking for. How much ammonium must come from this ammonium chloride so that when I work this all out, I get the pH level that I'm looking for. And I have 0 of that to start with. So that's what I have to start with. Now, I know a pH. Well, if I know a pH, then I know a concentration of H, and you should know how to calculate that. So I'm going to jump right to that. If you can't figure out how to go from pH to concentration of H, go back and review some of my other videos, especially the ones from pre-AP. They would work there. Okay. Or what if I don't necessarily go to concentration of H? What if I go from pH to pOH? I could do that way too. So whichever way you want to go, the point is in the end to get to OH minus, and you have options. You can go from pH to H to OH, or from pH to pOH to OH minus. So let's just start with the easy subtraction. 14 minus pH gives us pOH, so my pOH is 4.85. Then again, review it on your own if you need to. Well, that didn't work. Come on. Okay. Review it on your own if you need to, but turning that into my OH I find is 1.4 times 10 to the minus 5 molarity. Now, what is significant about that is that that is my final, that's my at equilibrium concentration, that's my, at the end of the problem, my OH minus is that concentration. So I can right now, at equilibrium, at the end of my problem, I can write that number right here because that is what that number is. And now we do some quick little math. Hey, if I started at 0 and I ended at that number, what's got to be in the middle? Well, I've got to have gained 1.4 times 10 to the minus 5 molarity. And if I gain 1.4 times 10 to the 5 molarity there, what did I gain here? What did I lose there? Hey, look at that, it's a 1-to-1 ratio, which often is the case, but check your ratios anyway. So I gain that much there, and I lose that much here. So now check out what I can do. I can do some addition here, and I can do some subtraction here. Now I point this out. That is a very large number compared to that number. So I don't even need to say I'm going to assume by the time I subtract around to sig digs, I've got that same number I started with. So that's just normal subtraction and rounding to sig digs. Here, again, this is a really, really, really small number, and I have a feeling I'm going to need a rather comparatively large number here. So I'm going to assume that even though I'm going to add that little bit to it, it really is not going to affect my starting amount by any significance. So I'm going to call that x. You are welcome to do x plus 1.4 times 10 to the minus 5 molarity there. What difference will it make in your end result? Well, I've worked it and like almost none. Okay, so whatever you feel like doing there, but I have limited room on my screen, so I'm not going to do that. So Ka is concentration. Oh, what did I do wrong? I said Ka, and this is a Kb. I hope you were yelling at me for that. Okay, so this is a Kb, because I'm going to have NH4 plus and I'm going to have OH minus, and you want to be absolutely certain that when you have that OH minus that you write a B there. Now what's even better, don't write anything at all, and then you can't get penalized for writing the wrong little letter there. Because all K's work the same. We don't have to specify what K they are. And I doubt they would ever ask you to specify what kind of K you have in this equation. Okay, so moving on. I've got to pick up the pace a little here, so I'm going to plug in my numbers x and 1.4 times 10 to the minus 5 molarity and divide it by 0.10 molarity, and that is equal to Kb. Okay, I need a Kb. What do I do for a Kb? Okay, well, this is working with ammonia. Okay, and so we would look up a Kb for ammonia, which is 1.8 times 10 to the minus 5. Okay, so again, you know, on homework and stuff, you would look it up on tests, on quizzes, on the AP exam, it would be given to you. Solving for x. And the real reason I'm solving for x is to find the concentration of ammonium that I originally started with. See where my x is? Okay, this x corresponds to that x. That tells me the original concentration of ammonium is going to be 0.13 molar. All right. Have not answered the question yet, though. That's the concentration of ammonium. I'm looking for grams of ammonium chloride. Well, to get 0.13 molar, I need 0.13 moles of ammonium chloride, because it's a 1-to-1 ratio, in 1,000 milliliters. That's what that number is. But in this solution, I'm only using 500 milliliters. Okay. So now I know how many moles of ammonium chloride I have. But I don't want moles of ammonium chloride. I want grams of ammonium chloride. So I say 1 mole of ammonium chloride is, and I just start adding things from the periodic table, and I get 53.491 grams. Way more sig digs than I need, but that's the way I roll. And when I round to sig digs, in the end here I get 3.5 grams. That is the grams of ammonium chloride I would add to 500 milliliters of NH3 to make a buffered solution at pH of 9.15. So I know that question, you looked at that going, how do I even begin that? Well, check that out. We started with our equation. Always a great thing to do. I filled in my rice table, putting the x where I didn't know, and I filled it in because I was given a pH. I could do that. Well, once I have a completed rice table, I can plug it into a K expression, and I looked up my missing K value, and I found the concentration of the ion. Well, that ion would come, it's a 1-to-1 ratio between ammonium and ammonium chloride. So I just figured out how many grams of ammonium chloride it would take to get that concentration of ion, and there I go. So it really is not a difficult question. Now, did that take time? Absolutely. But it's not a difficult question once you get familiar with these types of acid and base type of questions. Okay, let's talk about this. We want the pH of a solution attained by mixing 400 milliliters of a 0.200 molar acetic acid solution and 100 milliliters of 0.300 molar sodium hydroxide. First off, very different than we've been doing so far, because this is a neutralization reaction. I am neutralizing acetic acid with some sodium hydroxide. Now, I don't know if I'm neutralizing completely to get to like 7. I may not ever get to 7, even if it is neutral. But that's what some of the acid and some of the base is going to react to give me a salt and water. So let's focus with an equation. Sodium hydroxide and acetic acid, which is HC2H3O2. One-way arrow, because I have a strong base, it cannot go backwards. So one-way arrow is going to give me HOH, double replacement reaction, HOH, and NaC2H3O2. Now I'm also noticing, and I hope you caught this too, I'm mixing solutions. So I have dilution. So I need to account for the dilution as I work this problem. So I'm going to work in moles. So that many milliliters of that much molarity and that many milliliters of that much molarity. Wow, that's almost a tongue twister. Okay. So when I mix those together, I'm going to work in moles until the very end of my reaction. So I'm wanting to be sure I have the right amount of zeros going on here. So 0.0300 moles of that. And of my acetic acid, 0.0800 moles of that. And I would start out with 0 of that and 0 of that. Now I have a limiting reactant situation, as it's a 1-to-1 ratio. It's super easy to figure out. I'm going to run out of sodium hydroxide first. And it's a 1-to-1 ratio, so whatever I use up there, I'm going to use up there, and I'm going to add over here. And that says moles if you can't read my writing. Yep. And so, well, that didn't work. And so at the end, 0 sodium hydroxide remains. I have 0.0500 moles of acid remaining. Now that's moles of acid in a total of 500 milliliters. So I'm going to divide by 0.500 liters. I have water, don't care about water. And I have sodium acetate. And that's sodium acetate moles in 0.500 liters. Okay. So when I do this math, what I actually end up with is a 0.1, okay, let's do some sig digs, 0.100 molarity there, and a 0.0600 molarity there. All right, so I have my molarities. I counted for the dilution by dividing by the total at the end. I worked in moles till my reaction was complete. So I've mixed this base and this acid. I have not put enough base in. It's not, I have some leftover acid. It's going to be acidic. But how acidic is it? What's my pH going to be? Well, now we actually need to do like a rice table to figure that out. Because I have a weak acid, and I can't just say, oh, my acid will ionize completely, because it so won't. Plus, I have a common ion going on. Okay. My common ion is my sodium acetate, which is so totally going to give me some acetate ion. So I'm starting with 0.0600 molarity of that, and I'm starting with 0.100 molarity of that, and of course I have none of that. And I'm going to lose X, and I'm going to gain X, and I'm going to gain X. It's a 1:1:1 ratio, and because Ka for acetic acid is 1.8 times 10 to the 1.8 times 10 to the minus 5, I can avoid the quadratic. I would assume and avoid the quadratic. So 0.100 molarity, X, and 0.0600 molarity. So now that I have my rice table done, I write my Ka expression, which is 1.8 times 10 to the minus 5. Believe it or not, I've tried everything I can to keep the pen from moving the screen, and I just don't know how to turn that off. I blame Microsoft for it. 0.06x, 600x divided by 0.100. Those are both molarities, but that cancels. And X, which is concentration of hydroxide, is 3.0 times 10 to the minus 5 molarity. Okay, so that's the H plus ions that I have, and so my pH is the negative log of that, and so when I stick that into a calculator I get 4.52. And there's my pH. So I've not added enough of my base, even though it's a strong base and a weak acid, I've not added enough of my strong base to neutralize all of the acid, so my pH is still in the acidic realm, which makes sense. But it's not just a pure acid realm. I also have a common ion effect, a buffer going on, so it's going to be slightly higher than if it was just the pure acetic acid. Okay, so that's how we do that one. Let's try this one. What is the concentration of 25.0 milliliters of ammonia solution if it took 30 milliliters of 1.0 molar hydrochloric acid to titrate it to the equivalence point? Oh, equivalence point. When I hear equivalence point, I think railroad tracks, because I'm doing a titration. Okay, so I'm titrating, so I really just need a railroad track. Now let's focus. Hydrochloric acid is being added, which I know of. It's being added to some ammonia, NH3, which I don't know. One-way arrow, because hydrochloric acid is a strong acid. It's going to give me ammonium ion and chloride ion. Isn't that fun? So what do I know? I know it took 30 milliliters of 1.0 molar HCl, so that's 1 mole of HCl in 1,000 milliliters. And I know from my reaction here, 1 mole of HCl will neutralize 1 mole of NH3. And I know that I had 25 milliliters, or 0.025 0 liters of NH3 in my flask. So milliliters cancels milliliters, moles cancels moles. I get moles per liter of NH3. Hey, that's molarity of NH3. Hey, that's what I was looking for. So I'm ready to do the math. And I see that it was a 1.2 molar solution of NH3. So titrations, hopefully you realize by now, don't involve a rice table usually. Normally it's just a railroad track. You certainly do want your balanced chemical equation to focus you on what you're working on. So that would be the first step to writing that. Okay, we're coming back to this thought in a moment, but after this is titrated, when I get to the equivalence point, what is the pH? And I know you're tempted to say, well, if my acid and my base have neutralized, should it not end up at 0? Well, I want to point this out. No, it will not. And first off, I can even say, since I'm using a strong acid and a weak base, I'm going to have the neutralized level be actually acidic. I expect the pH to be less than 7 in the end. But here's how it actually is going to work out. Here's why. My HCl, when titrated with my NH3, is going to give me NH4 and Cl minus. What I care about is this ammonium. So watch that ammonium as we work. Now first off, we're doing a dilution. So I'm going to work in moles. So I'm going to take the numbers from before and I'm going to work in moles. So 0.03 moles and 0.03 moles and 0 and 0. And it's a 1-to-1 ratio, and so I lose 0.03 moles, I lose 0.03 moles. Well, that's good because we've neutralized. We've done a 1-to-1, 1-to-1 ratio. We've canceled it all out. So I'm gaining 0.03 moles, and I'm gaining 0.03 moles of that. Now, what I really care about is that I have gained 0.03 moles in a total of 0.055 liters. I have gained 0.55. I want to be sure my zeros are right. 0.55 molarity of NH4 plus. Because what's going to happen? This salt, remember when we talked about can salts change pH? This salt is going to change the pH now. The ammonium, as it floats around after being made from the neutralization, is going to find some water. And it's going to donate a proton to the water and reform some ammonia and some, well, H3O plus in the process. Now I could take water out, but I just feel like having the water left in. To what extent is this going to happen? Well, I have 0.55 molarity there, and I have 0 of that, and I don't care about that. And I have 0 of that because I've already neutralized what I thought I had in the beginning. Okay? And I'm going to lose X, and I'm going to gain X, and I'm going to gain X, and I'm going to make the assumption, and I want to point this out. How do I know I could make the assumption? Because I look up Ka of NH4 plus, and the Ka of NH4 plus is 5.8 times 10 to the minus 10. It's extremely small, so I definitely can ignore the X there. So I write my Ka expression. I'm going to solve for X. What I really care about is this column. Notice how X is concentration of acid, of hydronium ion. And so I can make my pH calculation there. So X, which is concentration of hydronium ion, I mean, I've done the Ka so often, you should be able to do that without me showing it. I get a 1.8 times 10 to the minus 5 there, molarity. Then I find my pH, and my pH of that is 4.75. So even though I have quote-unquote neutralized my weak base with some strong acid, the salt I made in the process is going to react in a side reaction and still act like an acid and lower the pH. So not surprising that strong acid and weak base leaves it even at a neutral level below 7. Even though I've neutralized it, quote unquote neutralized it, I'm not at 7 neutral. You kind of need to get away with the thought that neutral must mean 7. Because neutral only means 7 if you're talking about the autoionization of water at 25 degrees Celsius or a strong acid and strong base with equally matching Ka, Kb's at 25 degrees. In other words, neutral most of the time does not at all mean 7. It's just what we put there in the middle, and for lack of a better word, we call it neutral. Okay, so now that we know what it is at the equivalence point, I have a couple more questions for you. So on the next slide, we're going to look at what would be at the half equivalence point. And I'm hoping already in your mind you're saying, hey, what in the world is a half equivalence point? Please listen very carefully. The half equivalence point, as you would think the name implies, is halfway to the equivalence point, but that halfway mark is measured in terms of the volume of titrant. So we're talking half of the milliliters needed to get to the equivalence point. Well, our titrant is hydrochloric acid in this case. That's what's in our burette. And our unknown ammonia was in the flask underneath where it was going to drip into. And we know from earlier, if you go up a couple questions, the equivalence point took 30 milliliters of hydrochloric acid to reach. So the half equivalence point is going to take half of that, or 15 milliliters, to reach. With that information, we are still going to start off with the same reaction we've been working with. Hydrochloric acid and ammonia are going to give us, sorry, that should be a one-way arrow because of the strong acid, are going to give us ammonium and chloride ion. And I really don't care about the chloride ion in the work that we're doing. So at the half equivalence point, I have 15 milliliters used of our hydrochloric acid. So I do a quick, I'm adding solutions. I want to deal with the dilution. So I want to work in moles. So I go through and I calculate, the volume times the molarity expressed as moles per 1,000 milliliters. And I see that I have 0.0150 moles of hydrochloric acid delivered into the flask, which, no surprise, is half the amount of moles that is needed to neutralize all the ammonia. So it's no surprise that it's half, because that's the whole point of a half equivalence point. And I'm starting with 0 and 0 of that. Now I certainly have a limiting reactant situation going on here, so I'm going to lose the 0.015 moles of that, and I'm going to lose, it's a 1-to-1 ratio, that many moles of ammonia, and I'm going to gain, I'm missing a 0, that many moles, and I'm going to gain that many moles of that. And so now, what do I have at the half equivalence point? I have 0 of that left. Okay, I really don't care about the chloride ion for my work, so I'm going to ignore it. I have 0.0150 moles of ammonia left over, and I have made 0.0150 moles of ammonium ion. These I care about. Now that's moles, and now I want to account for the dilution. So I'm going to divide by the total, be careful. The total volume is half of what I've added previously. So the total volume is, liters. Total volume is 0.040, okay, there probably should be another 0 there, liters. So I'm accounting for the dilution by dividing by the new total. And don't use the old total, because I've only added half the HCl, 15 milliliters. 15 milliliters from the acid. I had 25 milliliters already in the flask of base. That's 40 milliliters total. Okay, so I find the molarity here, and what I end up with is 0.375 molar. And what I end up with here is, imagine that, I get another 0.375 molar. Now I'm ready to actually find my pH. And I do have I guess I'll go red. I do have a weak base and its conjugate salt going on. And so with that weak base conjugate salt, I could totally use the Henderson-Hasselbalch equation here and just, one calculation, have my POH and then turn that to my pH. But I'm going to do it with the Rice table just to continue the demonstration of that. So ammonia will react with water. You really won't know what's going on unless you add the water in. Okay, ammonia will react with water to grab a hydrogen off water and make ammonium ion, and we have left over hydroxide. So now how much are we starting with? Well, I don't care about anything about the water. I'm starting with 0.375 molarity of that and 0.375 molarity of that, and I have 0 hydroxide to start with. Okay, so how much am I going to lose? I'm going to lose X. How much am I going to gain? I'm going to gain X. So I look at the Ka for ammonia, okay, and that's 1.8 times 10 to the minus 5. And so I can totally ignore the added X here and the subtracted X there. So I have 0.375 molarity, and I have 0.375 molarity there, and I have X there. So I can certainly make the assumption and avoid the quadratic. And if you don't believe me, then use the quadratic equation and see what difference it makes. Go for it. So when I do all this and I solve for X, it turns out that X is 1.8 times 10 to the minus 5 molarity. Well, what good does that do me? Well, be very careful here. X is the concentration of hydroxide ion, which means I can find a POH. And it turns out when I take the negative log of concentration of hydroxide, which is that, okay, so negative log of that number there, I end up with a POH of 4.74. So we're on the basic side, which means now the question asks for pH, so I'm not done. So 14 minus that, I get a pH of 9.26. Okay, so there's my final answer at the half equivalence point. Okay, and I got to the half equivalence point by adding half the milliliters of acid needed to get to the total. Do I need to know how much I need to get to the equivalence point before I can find a half equivalence point? Absolutely. But that's what we do with it. We find the equivalence point, then we calculate what was it at the half equivalence point. Okay, so now let's finish this off with what was the original pH of the pure ammonia solution. Okay, well, when I have nothing but ammonia going on, ammonia and water would give me ammonium and hydroxide. And I started in the little flask. Okay, I don't know what I started with in the little flask because that's what I did my titration to figure out. But if you go a couple questions up, we started the series with ammonium and hydrochloric acid with how much was the starting amount of that ammonium. And we had as an answer 1.2 molarity. Okay, and I really am not going to care about the water. And we're starting with no acid or anything going on. So I have no ammonium ion and I have no hydroxide ion. And I'm going to lose X and I'm going to gain X. And I would make the assumption, so 1.2 molarity, X and X. Don't know where my M went. Okay. So we make the assumption to avoid the quadratic. I would solve because Ka is still 1.8 times 10 to the minus 5 for ammonia. Okay. And when I solve for X, which what I care about X is that it's an OH minus. Okay. That is 4.6 times 10 to the negative 3 molarity. And so now from that I can find a POH, negative log of that number. Go figure, it's going to be, less than 3. So I get 2.33. And I'm going to turn that into a pH by taking 14 and minus that. And this makes sense because I am working with a base. Ammonium being a proton acceptor is a base, and I get a pH that's in the basic region. And I do expect ammonia to be a weak base, not a strong base. That's why we're using those equilibrium arrows. So there's my pH to start with. Okay. One of the things they love for you to do on the test is to do a titration curve. Either make it or add to it or label it or discuss it. So let's take care of that. What is a titration curve? Well, a titration curve is an axis. And your axes are always going to be pH on the y-axis. So we need like a 0 to 14 mark. Halfway through is 7, and I'm going to kind of half of that is 10.5, and half of that's 3.5. Okay. And more than likely on the test, they would like give you the axes already like labeled and have some grid for you to even, be more precise with. But it doesn't matter. I can draw it, and I know you're awed by my artistic ability. Yeah, not, right? Now down here is always going to be the volume of titrant. What that is in our case is milliliters of hydrochloric acid. But it's always going to be the volume of what's dripping out of your burette that we put on the bottom here. So I start with 0 dripped out of my burette, and I have already found out that the equivalence point is going to be at 30 milliliters. So I'm going to put that in the middle of my graph, and that's kind of standard practice. If you know what the numbers are, it's rather standard practice to put your equivalence point in the middle of the graph. When we do it in lab and you don't know what that's going to be, you just graph what you have data for. Okay, now let's put this all on the graph. We have to go back. You're going to look up, or back in your notes, several questions. My original starting amount, which we just determined, my original starting amount is probably like right about here. That is 11.67 on the pH scale. Okay. My equivalence point, and here's the catch, my equivalence point is not neutral. We had that side reaction going on that we calculated a pH with, and it ended up being like 4-ish. Okay, so you go back, you look up the number, and it's somewhere right around there. There's my equivalence point. Okay. We also had a half equivalence point, which meant half of the volume of titrant. So my half equivalence point's at 15 milliliters, and we determined that was 9 something. And you go back up and you look at what that was, and I'm going to guesstimate that to be right here. Now, they're not picky on the test about how your actual graphs look, but there are some key characteristics for a titration curve. So please, please, please catch what I'm about to show you as key characteristics. First off, it is never a smooth, it's never a straight line. If you have a straight line for a titration curve, you've done it wrong, because the name should imply it's a curve. It's a curve that normally has a rather flat start, and then as you get to the equivalence point, it's going to nosedive and then pull up and do something like that. And that's a fairly standard, generic titration curve looking thing, and I know you're just awed by my artistic ability, but don't worry, they don't hold you to the level of artistic ability that I have maintained. Okay, but what are they going to look for? They're going to look for that you started where you said at 11.67. They're going to look that your half equivalence point is where you said around 9. Okay, we look up and you can be a little more specific. That the nosedive occurs right at the equivalence point. This is a key characteristic of when we neutralize acids with bases or bases with acids. The equivalence point, there's that very super fast change in pH before and after. Okay, so they're looking for, do you start and hit those 2 points? Do you kind of go straight in the nosedive at the equivalence point? And then where do you end? Well, I'm adding hydrochloric acid, and eventually at this point I have used up all my weak base. So now what's going to happen to my pH as I add more and more and more, like let's say I go out to 45 milliliters. So by the time I'm at 45 milliliters, I've used up all my base. And I'm simply adding acid to what is still acid. So I'm adding more and more and more acid, so the pH I expect to end very low, because hydrochloric acid is a very strong acid. Okay, so this would be very typical of a weak base. Notice the pH starts rather, low on the pH scale in terms of bases. So weak base area, it's a weak base. quick nosedive when we get to the equivalence point, not at neutral. We already discussed that. And then it ends very, very low on the pH scale because hydrochloric acid is a strong acid. Now, what if it's not that kind of case? What if it's like strong acid with strong acid, or weak base strong, or weak base weak acid, or any combination? Well, actually, that's our discussion for topic of next time. We're going to go through a whole bunch of graphs and analyze them. But let's pause here, and that's enough for today. I hope you really have been pausing and calculating ahead as much as possible and seeing how well you can do these, but certainly to be sure that you are good with them, we're going to practice. So good luck on your practice.